Okay, so I discussed the mathematical operations on vectors, but now let's show some physical applications. So first of all, in principle, at this level, we can say that the physical quantities, I will show you examples what quantities are in a minute. They can be divided into scalars and vectors. Okay, so what scalars are just regular numbers. So you care only about the value. For example, time, temperature, mass, electric resistance. So you only want to know how much time, what's the value of temperature, what's the mass, what's the resistance of a bulb, say. But in vectors, you know, we are discussing vectors, you know that they are arrows, so not only value, so not only length of a vector, but also the direction matters. So, for example, the displacement or position, the better displacement or velocity. So in which direction the car goes with some velocity. The acceleration is also a vector. A force, which we will discuss in a later chapter. I told you that this is basic way of dividing the quantities, because in theoretical, more advanced physics there are also 4 vectors, there are also tensors, so other kinds of mathematical objects which behave differently, but this is again beyond the scope of this video, so here we just focus on scalars and vectors. In my video about speed, distance, time, I really tried to say speed and not velocity. Hopefully I managed, because you know, in everyday life speed and velocity are kind of synonyms, but sometimes you want to distinguish these two terms. So let me show you what is the difference and what is the formal definition of velocity. So let's think of our example of ant which is walking on the floor of your room. So suppose you observe an ant here and you see it walk some crazy way and final, so let's say it starts at point A and after some time you find it after this way to be here in B. Okay, so speed, as we calculated in previous video, is s over t, and s is a distance, so you measure all the way of the ant and divide by time in which it walked this distance. So this is speed. And now about velocity. So now we can, let's say this is origin of our coordinate space, so this is x-axis, y-axis, okay, of the ant. This is RA, the position of the initial position of ant, and similarly you can have the vector RB, the final position of the ant. So here this is the displacement between initial and final position of the ant. Let's call it delta R. Delta r. So this triangle is actually the capital Greek letter delta, and always in physics this delta means change of something. So in this case, displacement, so delta r is change in position. So this is final position minus initial position. Okay, and you can see that you know how to subtract vectors. So you have RB, and to the end of this RB you can put minus RA. So something like this, minus RA. And if you connect beginning of RB with end of minus RA, you get the very same vector delta R like this. You have nice parallelogram. So now this was speed, and now velocity. Velocity is defined as a vector, as a delta r, so change in position or displacement vector divided by time. So the value of this, so value of vector you denote like this means value, and often we write this just by v, but for short, but or for any vector, for example length of a, we just denote by a. But here we will not do this because we don't want to mix with v, which is speed. So here v as velocity vector, so you see that displacement is much smaller than the distance along the trajectory of the ant. So it will not be the same thing. So this is velocity. And in this case, value of velocity vector will be of the average velocity vector will be, of course, smaller than average speed. So the velocity is defined as the change of the position vector in time, and similarly the acceleration is also a vector which is defined as change in velocity vector in time. Alright, so I told you that the acceleration vector is defined as the change of the velocity vector divided by time. And surprisingly, this definition brings us to two different kinds of acceleration. So let me show it to you. So the first is pretty obvious. So suppose this is a road and this is a car, and first it goes with speed v1 30 kilometers per hour, and after some time somewhere further it goes with speed 60 kilometers per hour. So you have acceleration because speed changed, or the I mean the instant speed changed. So the length of the vector changed, so of course you have acceleration, okay? Because as with position, delta v is final speed or final velocity minus initial velocity vector. So because the length changed, then of course it changed. And the second situation, let's say there is a curve and we look from the bird's view from top, and the car first goes with speed v1 30 kilometers per hour, and then it goes like this, and then it goes again with speed v2 the same 30 kilometers per hour. So the value of the velocity didn't change, but surprisingly we still have acceleration, because in acceleration we have change of the vector. And look, in the beginning the vector, the length of the vector didn't change, but the direction of the vector did change. So if you draw this v2 like this, and this v1 like this, you can subtract these two vectors and get some vector delta v. So let's do this. So v1 I put here, but I should have again v2, you remember, plus minus v1. So minus v1 is something like this. Okay, and the result of v2 minus v1 is, oh boy, is this. So this is delta v in this case. So somewhere between these two situations, vector delta v is pointing this direction. So look on this. So we can write it as 1 over t times delta v. T is time, it's some value. So 1 over t is some number which is of course positive because time is positive. So you, given vector delta v, you just multiplied it by 1 over t. And remember, as I showed you in my previous video, multiplying a vector by number just rescales it, but it doesn't change its direction. So if delta v is pointing in this direction, vector a, vector of acceleration, will also point the same direction, but it will be longer or maybe shorter. So it points to the center of this turn of this curve. So it's called the centripetal acceleration. I will go back to this when I will discuss the circular motion in more detail in my next videos. I think I should stress one thing about this difference between speed and average value of velocity. So again, speed v, distance over time, and value of velocity, value of vector v, value of displacement, change in position over time. So if you have such a winding trajectory with so many turns, then of course distance is different, is very different from the displacement. But the more straight is the trajectory, or the shorter piece of trajectory you choose, they will be these quantities according to these definitions will be closer. So suppose we focus on this piece of the trajectory and we zoom in, let's draw it larger. So say this trajectory is something like this. So on blue line we measure distance, and the displacement in this piece would be the straight line like this. So this will be this has a length of length of delta r. So the shorter it is, the closer these two become. And again, in jargon, in everyday life, we usually treat speed and velocity as synonyms, but sometimes very formally we can distinguish between speed and average value of velocity, defined like this.